Good evening and welcome. If you've joined us tonight, you're probably passionate about airplanes. However, have you ever wondered what it takes to design and build a UAV that flies autonomously for hundreds of miles to deliver a payload? We are excited to showcase just such a project, the design of a next generation uncrewed air vehicle. Our goal is to distill thousands of hours of work into 20 minutes of highlights. We also welcome your participation. Please use the Q&A button to share your questions. You should find this button near the bottom of your Zoom screen. Next slide. My name is Dr. Brian Roth, and I'm a professor of aerospace engineering at Embry-Riddle Aeronautical University. Over the years, I've had the privilege of being a part of a number of aircraft design projects. Early in my career, working on contract for NASA and on projects for DARPA, and more recently for commercial aircraft manufacturers such as Boeing and Lockheed Martin. But this evening, I'm excited to share with you a project that we're doing in partnership with General Atomics. Next slide. General Atomics approached us last summer, approached us at Embry-Riddle and asked if we'd be willing to design an aircraft for a particularly interesting and challenging mission, as illustrated here. Imagine a mission where a small UAV, shown in image number 2, is dropped from a larger UAV, shown in image number 1. And perhaps there are several of these smaller UAVs dropped from a large UAV. To facilitate that, we need to fit the small UAV into a width of no more than 24 inches or 2 feet. And yet, to accomplish our mission, we need a wingspan of greater than 10 feet. So that's one interesting design challenge. Our wings need to fold. Once our UAV has been dropped from the larger host aircraft, the wings unfold and it begins its mission. The goal is to fly for at least 3 hours, at least 150 nautical miles, and to deliver 2 5-pound payloads of medical supplies to someone in need. That was a design challenge that General Atomics posed to us. And to meet that challenge, we developed the following team, as shown on the next slide. We structured our team much as an industry partner would. We have 16 students and 2 professors, 1 industry partner. And our structure includes a project manager whose role is to organize our work to make sure that we're staying on time and on budget. We have a chief engineer, also a student member of our team, who's responsible for technical progress, providing the resources that each member of the team needs to be successful. And then the rest of our team members participate in one of several IPTs, or integrated product teams. We have an IPT focused on aerodynamics, the aerodynamic performance and the stability of our aircraft. Another focus area is on systems, tracking our performance requirements and making sure that we're checking those off, that we're meeting all of our customers' requirements. We have another group dedicated to manufacturing, to planning for the manufacturing of our flight test article. We have a structures team dedicated to design the internal structure of our aircraft to make sure that it's flight worthy. And last, we have a propulsion team focused on the propulsion system, the engine of our aircraft. So we have our mission, we have our team, and on the next slide, we'll give you an overview of our design process. Our process is designed to model the same steps that you'd see in an industry project, but on a compressed timeline. So a typical industry project might be 12 to 24 months for a small UAV, whereas we're confined to a 1 year, 2 semesters. So we began our work last fall, looking at system requirements. We were given a short system requirements document from our sponsor, and to that, we added such requirements as those provided by the Federal Aviation Administration, or NATO. Once we knew exactly what our vehicle needed to accomplish, we entered a really fun phase, a creative phase, a brainstorming phase, where we generated lots of different design ideas on how we could accomplish this mission. And that's illustrated in the little hand sketch at the bottom. We quickly narrowed down those concepts from crazy to more realistic, down to 3, which we shared with our sponsor in an interim design briefing. And based on their feedback, we further narrowed our focus to a single design presented at the middle of our project during our preliminary design review. In spring semester, our focus was on prototyping and testing, ensuring that our major subsystems, our most complex parts worked as designed. And then we finished up our project by building and flight testing the full aircraft. Let's take a closer look at each phase of the design process, guided by Max Welliver. Next slide, please. So Max Welliver is a senior aerospace engineering student here at Embry-Riddle. He's also a private pilot with a seaplane rating. Over the past few summers, he's been an intern with the Boeing company and plans to return in the role of flight test director after graduation.
Awesome. Thanks, Dr. Roth, for the introduction. And so now that we kind of have a bit of background on the project, first we're going to take a look into the conceptual design phase, starting with an aircraft sizing code that we'll look at here on the next slide. All right, so what you see here is a framework for a MATLAB code that our team developed primarily during our first semester of the project. And MATLAB, just to give a little bit of background, is a coding language that all of the engineering students at Embry-Riddle learn how to use their freshman year, and then we use it for our whole entire time at Embry-Riddle. So what you're seeing in this picture here, so all the red blocks are representing a piece of code that our team has developed. And then everything else that you see is either an input or an output into this code. So starting off in the top left corner with the controls code, first we feed it some inputs about the airplane's geometry. So some initial sizing parameters. So think our wingspan or our wing area, and then a few other parameters there. Then plugging those into the controls code, we get some outputs. So we get information about our tail sizing and control surface sizing. So ailerons, elevator, rudder, how big are those control surfaces going to be to make the airplane fly. And we take all of these parameters and plug those into the structures code. So we're taking these inputs in the form of volumes. So we have a lot of different volume that we've just created on this airplane. And we want to see, well, how much is it going to weigh? So the structures code applies different material densities and outputs a total weight for the airplane. And it also outputs a center of gravity estimation based on mass properties of those critical components in the airplane. So then we take that CG value and plug that into the stability code, which you see down in the bottom right. And that stability code will output a static margin, which helps us understand how is the airplane going to behave. Is it going to be stable or unstable? And then if we go up just a little bit to the aerodynamics code, once again, we're taking in all that aircraft geometry again, and the aerodynamics code is going to output the drag values for the airplane. So how much drag force is it producing, and also what's the coefficient of drag? And taking those values, we can send those into the propulsion code, which you see there sort of in the middle of the screen. And that propulsion code will take in that drag value and say, okay, how much thrust do we need to provide the airplane in order to fly with that much drag? And then finally, we take all those inputs and put them into the performance code, and that will give us range and endurance of the airplane, stall speed, other performance characteristics of the airplane. So this is a pretty complex code, but it was a great tool to rapidly iterate through many different designs and then have an understanding of how they may perform. So this helped us narrow down our design pretty quickly in the first semester. And we can move on to the next slide, please. So once we had a design that we were happy with, we ran through a bunch of different analysis tools, and we're going to highlight some of those here. So first, you see some aerodynamic analysis that we performed using CFD, or computational fluid dynamics. And if you look at the top image here, I want to direct your attention to the tail end of the airplane. You'll see that the horizontal stabilizer is located kind of in the middle of the tail boom. So think of your conventional configurations for tails. So a 737 or a 747, any of those have a conventional style tail. And what we're seeing in the red lines here is those red lines are outlining a wingtip vortex that was forming on the inboard edge of our wing. And we were finding that this vortex was interacting in a negative way with our tail. So we were losing a bit of tail effectiveness. So using the CFD, we found that we needed to change our design a little bit. So if you look at the bottom image now, you'll notice that the horizontal stabilizer has now been moved to the top of the tail, and we call this a T-tail design. So if you know what the C-17 is, that's a great example of a T-tail. But you can see here that the vortex is no longer interacting with the tail. So we were able to solve this problem and maintain tail effectiveness at this critical cruise angle of attack that you see here. So along with aerodynamics analysis, we also perform some structural analysis that you'll see on the next slide. Yeah, so here you see what's called FEA, or finite element analysis. And what we're looking at here is the left wing. If you can kind of see there, there's a mini airplane image and the view that we're looking at. And on the left side of your screen, the blue end, that would be fixed to the fuselage. And then the red end is the wing tip. And we here are simulating a 6.75 G loading case on the wing. So if you think of your fighter jets, pulling 7, 8, maybe even 9 Gs, that's a lot of load on that wing. And we wanted to simulate something similar to ensure that our wing could withstand the deflection. So if you look at the color graph on the left side of your screen, you'll see that these represent different inches of deflection. And if we follow that color, that red color out to the wingtip, we see that at almost 7 Gs, the wingtip is deflecting only about 1.7 inches. So this is a pretty stiff wing based on how we designed it. So the spar components on the inside, the ribs, and then the material selection that we chose all helped keep that wing very stiff. And so this was a great confidence booster. And once we did this, we were very happy with our design. So this was just one of many analysis tools that we used along the way. But once again, once we were happy with our design, we then were able to move on to manufacturing. So let's move to the next slide. Perfect. Thank you. So here, what you're seeing here is our fuselage molds. So we cut our fuselage into 2 halves, and then we 3D printed these very large molds. So there's 6 pieces each. And the plan here was to lay up our carbon fiber skin over these molds. And if we play the next video on the next slide, you'll see this happening in real time, or pretty quick, actually. So you'll see us laying these carbon fiber sheets over the mold. As you can see there, we did 3 layers of the carbon fiber sheet, and then we are adding resin to it to harden that skin. So it takes about 20 minutes for the resin to start to harden, and then another about 8 to 9 hours for it to fully cure. So you can see we just moved it over to what's called a vacuum bag. And so we are basically sucking all the air out of that bag and trying to get that skin to form as closely to that mold as we can. And then if we move to the next slide, we can see kind of what the outcome of that is. So on the left side, you see 1/2 of that fuselage, so the fuselage shell, and we've already started to install some of the internal components. So we used a lot of different materials in there, and then you can see a carbon fiber tail boom that's extending to the aft of the airplane, and then the tail is mounted back there. So a lot of manufacturing hours were put into this airplane. And if we go to the next slide, we can see what the final product looks like. So I'll actually give you the number. It was over 1,600 hours of manufacturing time spent on this model that you see here. So we were very proud of the final product, but we couldn't quite flight test it just yet. We still had to do some pre-flight testing. So to give you an example of one of these, you see a landing gear drop test. So we pick the airplane up a few inches off the ground and drop it to simulate a really hard landing and see if our landing gear can take that load. And then that wooden dowel that you see extending from the nose of the airplane, that's to represent our propeller. And the goal here was we did not want that dowel to strike the ground, which would have meant a prop strike in the event of a hard landing. So we passed this test, and then we did a bunch of other different tests too before our flight testing. And we'll jump back in on the flight testing here in a little bit. But first, I'm going to give it back to Dr. Roth to introduce our communications professor for the course.
Thank you, Max. As Max noted, we've invested thousands of hours in bringing this UAV to life, and it's definitely not a one-person job. Teamwork and communication are key to success, and that role is led by our communications professor, Dr. Rick Mangum. So Dr. Mangum has been involved in Capstone design courses for over a decade, and been involved in some really interesting and fun projects. Last year, one of his teams won Best Tech Report for the 2024 Vertical Flight Society design build vertical flight competition. In 2020, he led a project with a team of students designing a Mars habitat with JPL as a sponsor. And he's also had teams designing meteorite core samplers that were tested in NASA's Neutral Buoyancy Lab. So Dr. Mangum.
Thank you, Dr. Roth. Just so I'll explain my role on the team or in the course. I work to support students in their communication efforts. So that includes oral presentations and written documentation. And there's quite a bit of documentation that goes into a project that requires 1,600 hours of development and build time. A successful project is really dependent on a team that knows how to work together effectively. We use Tuckman's phases of team development, which include forming, storming, norming, and performing. And really what we're after is we want to help the team get to that performing stage as quickly as possible so that they can start to really do that important work where they're firing on all cylinders. From day one, we incorporate team building exercises, activities, and reflections into the course. We conduct regular check-ins with students to gauge progress and comfort levels with the team. This year, we had a student employee work specifically with students as he mentored students in the teamwork process. Essentially, students get a lot of practice working in the teamwork environment. And that's one of the outcomes of the course, is that students learn how to work effectively as a team. Next slide, please. Another thing that we do is we have what's called a Capstone Symposium. And teams have two opportunities to really showcase their work at the Capstone Symposium. So there's a Capstone Symposium at the end of each semester, one at the end of the preliminary design semester, which is typically fall semester, and then again at the end of the detailed design semester, which in this case is actually coming up on Friday. Capstone Symposium includes a poster session and an oral presentation that offers teams 60 minutes to present their work and answer questions from industry panelists, faculty, peers, and other attendees. So the Capstone Symposium is really an opportunity to showcase the exceptional work that our engineering capstone teams are doing. And it's always a delight from a faculty perspective to see all the excellent work that our students are doing and just the uniqueness of the projects that they're engaging in. So now I'll hand it back to Dr. Roth.
Thank you, Dr. Mangum. So we've invested in design and analysis, in teamwork and communication, and now the moment of truth, flight testing. Will it work as we intend? Was our analysis work correct? To lead us through that flight test process, we're joined by Danielle McCormick. Danielle was our systems lead, tracking our progress and meeting those requirements, guiding our flight test plans. So Danielle.
Awesome, thank you so much. All right, before we jump right into the fun stuff of flight testing, on the next slide, I'm going to show you something that we use to keep us on track and making sure we were doing what we originally set out to do. So this is a test card that we use during our flight test process. And this is something we use to make sure we were staying on track in doing what was actually asked of us by the customer, not just doing something that we thought would be fun. Of course, this is all super fun, but we wanted to make sure that at the end of the year, when our customers asking us, where's our, how'd the plane go? You know, what happened? We wanted to make sure we could give them the best possible product. So something that on this test card is we used tasks. So this was a step-by-step list of what our pilot would perform in flight. Having this in sequence really helped us with our data analysis after the fact. So knowing that we were going to do a certain aerodynamic procedure at a certain time, and we'd mark that down with videos. We would have videos of the pilot, we'd have videos of the plane, all the sorts of different things, and we can compare that with the Excel that we got from our flight. Was really crucial before we got into flight testing. On the next slide, I'm going to show you, this is another way that we verified that our plane would perform exactly or very similarly to how we predicted it would. So this is a wind tunnel test. We had a scale model of our plane. This is mainly 3D printed, so a lot different material than our plane, but it's very, very similar geometry, very few differences. And this picture here is us doing a flow visualization test. So you can kind of see strings taped on all over the plane there, on the wing, on our fuselage, even on our tail. These did have a really important purpose. This showed us if our computational fluid analysis that Max talked about earlier was actually reflective of our actual design. So this is just verifying that the tests that we did and the analysis we ran actually matched up and was consistent with what we were seeing. Now we're going to get into the flight test videos. So this is of our first flight.
Let's go.
So as you can kind of start to hear there, our team is celebrating. This was the first flight we had, and this one was really crucial to actually proving that our design could take flight, what we had. This one, it was really crucial to us that we had all sorts of data collection as possible. One thing did go wrong the day of is that we didn't have live battery feed of the aircraft. So it was something we were super nervous about, is we wanted to make sure that our battery that was driving our propeller and the different control surfaces on the plane weren't going to give out while the plane was in air. So it was something we were super nervous about. So we did a lot of analysis day of and making sure that we knew what our battery capacity was and how long we could safely keep it in air. Next slide, please. This was a procedure called a low pass. And this one was really important to know that our pilot had full control of the airplane and knew exactly how it would fly before we got into some more of our complicated flight procedures, like our payload dropping test, our aerodynamic test, our stability tests. So making sure that our pilot had full control and knew exactly the kind of any sort of differences in this plane versus previous planes that he'd flown, and just making sure we had that all dialed in. Next slide, please. Speaking of interesting tests, this is a good one.
Sweet.
So that was our payload deployment test. That was the first one we did. This one was a really big moment because we didn't know exactly how our plane was going to respond with our 5-pound canisters suddenly being outside of the plane. So one thing about weight in planes is that it really determines how it's going to fly, where the center of gravity is. So that was all something we wanted to make sure we had as much data collection and as much visibility on as possible. Next video, please. And finally, this is one of our landings. So as you can see, our team was very, very excited to see it go up in the air safely, perform all the procedures we expected, drop a canister 5 pounds out of the aircraft, and also come back down safely. This was a very big deal for our project, and the whole team was super, super excited. And then a great thing from all this is that we got data from it, we can learn from it, we can say, oh, it did kind of this weird thing at a certain time on the video. We can look back at the Excel and we have all of those timestamps, so we can kind of figure out why it did what it did or what it was doing at the time. Thank you, that's all for me. Next slide, please.
All right, so now that you've heard about this amazing project, I'm sure you're all wondering, how can I be in these students' shoes? What can I do to become an Embry-Riddle student? So that's what we want to talk to you about now. And I want to start with the admissions process. So for us at Embry-Riddle, we do have a fairly straightforward admissions process. And the first thing that you're going to need to do is to submit the application. If you are currently a senior and you haven't applied yet, that's okay. We've got rolling admissions, so you can start this process now. For those of you that are juniors, you may consider applying this summer, which is when we open up our application for admission. Anybody who's younger than a junior, the earliest you can apply is going to be the fall semester of your junior year. So once you complete the application, and you can find that application directly from our website, we ask for some pretty simple information. We want to know about your educational background. We obviously need your contact information, fill that out and submit that to us. Now, before you submit, we will ask you normally for an application fee, but because you've joined us today for this webinar, we're going to give you this application fee waiver code. So while this is being recorded, feel free to jot this down as you're watching. DBPC is the 4-letter fee waiver code. Enter that in and it'll waive that $50 just as a little thank you for joining us here today. Now, in the admissions decision, we obviously need to look at your academic background. We need to make sure you're prepared to come into our program. So if you're a high school student, we will need a copy of your high school transcript with at least up through your junior year completed. If you're a transfer student, we're going to need a transcript from all of the colleges that you have attended. So that way we can assess your academic background, make sure you're prepared to come into our programs. We highly recommend that you submit to us 2 letters of recommendation, just so we can help get to know you a little bit better, see what some of your faculty members, some of your professors, your teachers, and your mentors might have to say about you. And then we do have some optional items. So we are a test optional institution at Embry-Riddle, which means we do not require the ACT or SAT test for the admissions process. It's completely up to you if you want to send those to us or not. And then the last optional item is going to be an essay or a resume. So with our rolling admissions process, once we get your documents for your application, we'll review it and hopefully we'll make an admissions decision, get you admitted to Embry-Riddle so that you can join us in the next upcoming start term. Now, some things that you should know about the application. With that rolling admissions process, I did mention an ongoing basis, but something to keep in mind is that as our programs grow, we are approaching capacity in some of those programs. So it's always best to apply sooner rather than later. Get your application in, send us your documents so we can get you an admissions decision and we can hopefully get you admitted into the program that you're pursuing. I mentioned that our fall 2026 application does open up in the summertime. If you don't want to get it done over the summer, then like I said, fall semester of your senior year is the best time to submit that. Now, once you've been accepted, we do review all of our accepted students for merit scholarship. So that's going to be scholarship that is just based off of your academics. So for incoming high school students, we're going to look at your high school GPA as well as those test scores if you do send us the test scores. And if you're a transfer student, then we're going to look at your college GPA. Starting point to be considered for one of these merit scholarships is at least a 3.0 GPA or higher. And scholarships vary every year, but on average, they can range anywhere from about $5,000 all the way up to about $20,000 per year. So it just kind of depends. Besides that merit scholarship from Embry-Riddle, we do highly recommend that students and families file the FAFSA, which is the free application for federal student aid. When you're filing FAFSA, go ahead and enter an Embry-Riddle school code. That way we can get your FAFSA information. And once we receive it, we will take another review of it to see if you're eligible for a need-based scholarship from the university. So merit scholarships are offered from Embry-Riddle and need-based scholarships are offered if you do file the FAFSA. But we also take external scholarships. We have some special relationships with organizations like First Robotics, Vex Robotics, Cyber Patriot, America Rocketry Challenge. So if you're involved in one of these organizations, you could apply for one of these special scholarships. It does have a separate scholarship application that you can find on our website. It requires the application to be filled out as well as an essay about your experience in these organizations. And that could potentially get you an additional scholarship. We offer a variety of these scholarships and it could be up to an additional $5,000 more. So great opportunities for your involvements in these organizations while you are in high school. And then lastly, external scholarships. We are an external scholarship friendly institution. So if you get a scholarship from a local organization where you live, if you apply to a scholarship that you just come across on the internet, great, apply for it. Hopefully you'll get it. And if you do, you can stack those up towards your cost of attendance in Embry-Riddle. So I know that was a lot of information in a short amount of time. I'm going to pop on over into the Q&A. So if you do have questions about admissions or scholarships, I will answer those there. And besides that, I will go ahead and hand it back over to our panelists.
Thank you, Sarah. So now we'll explore our kind of broader opportunities for participation on our campus and think a bit about how you might prepare for a project like this. And then we'll open it up to your questions. So the first question for our panelists is focused on our student members. How did you prepare for Embry-Riddle? And how would you recommend that high school students prepare to participate in similar projects?
Yeah, I can take that question here. So I think one of the excellent ways that you can get prepared for a project like this is practice working in teams. So I know in high school for me, I was heavily involved in different clubs and different project activities that helped me get a feel for how to work with a team, how to balance different personalities, and just how to function effectively to get the project done. So I think that's an excellent way to get prepared for college, but also your capstone design project, which will be a few years down the line once you get into college.
I absolutely agree with Max. I think focusing and learning how to work in a team and how to work with conflicting personalities and that kind of thing will really prepare you for success, not only in a capstone team, but throughout college as well. Like one thing about Embry-Riddle is that we really have a lot of project-based classes, everything. Every year you're going to have at least one group-based project in my experience. So really learning how to work with groups is going to prepare you not only for college, but for capstone.
Thank you, Danielle. You mentioned projects here on campus. Besides capstone, are there other opportunities for students to get involved in projects beyond the capstone and beyond the coursework?
There are so many opportunities on campus. Just one that I want to mention specifically is called the Rocket Design Lab, RDL for short. This is a student-led organization. It's considered a club. And in this organization, they do a lot of not only research, but also active participation into building different rocket engines and learning about the different fuel sources. And there's so many different projects you can be on in RDL, so you can really explore what you're passionate about.
Yeah, and I'll also add on to that another excellent club for the aeronautics focused people too. It's called DBF, or Design Build Fly, and this is a club that's actually at many universities. But what makes it cool is throughout the whole year you are working on designing an airplane and then building it, and then you go to a competition and fly it against a bunch of other universities. So Embry-Riddle has been participating in this club and this challenge for many years now. I think probably more than 15 years we've had airplanes go to competitions. And this is an awesome club to get involved in, even as a freshman. One thing they push heavily is for freshmen to step up into leadership positions. And this is great experience on how to lead a sub-team, like you saw here in Capstone, how we have many different IPTs, or integrated product teams. It's the same style format in the DBF club. So this is a great exposure, kind of like a mini Capstone is a way I've heard it described in the past. And it's a great way to prepare you for Capstone and get a lot of this analysis and just information about the design process before you even become a senior. So that's another great club on campus.
Thank you, Max. Question for all of our panelists. From your perspective, what makes the capstone design experience unique?
I think one thing that makes our capstone design process really unique is all of our time spent hands-on. This past semester, we've spent, like Max said, 1,600 hours collectively working and building our plane. And one great thing about what Embry-Riddle has is we have a spot like for us to work on it on campus with all of the resources we could need. We just need to order the very specific parts we decided we wanted on our plane. And that's our AXFAB. So that's our aerospace fabrication building. We have the machine shop that's open super great hours during the week. It has availability on the weekends, so we can really try to grind out our project as much as we can.
Yeah.
I'll add.
Oh, yeah, go ahead, Dr. Mangum.
Okay. I'll add that one of the things that makes our program unique is that most engineering students throughout the country will participate in some kind of a capstone experience. Some programs, the capstone is a semester long, some are 2 semesters like ours. But the thing that makes us truly unique is that we have 2 faculty members in the class. So we have an engineering faculty and then a technical communication faculty member, which is me in this case. And so we work together to build that teamwork with the team, to teach them how to write clearly, to communicate more effectively. And it's really, there's only probably a handful of programs in the country that do what we do. And I think that's one thing that really sets our students up for success, not only in the course, but also in the workplace when they graduate.
Yeah, that is also very valuable. And then to kind of answer this question as well, I think a super unique part is our ability to work with an industry sponsor. So, working with people who have done something like this before for real on a very large scale and with a lot larger timeline, it's a very great way for us to learn from them, learn their lessons learned, any information they can share with us about the industry standard process. That's been a super great way to learn from the best before we start to get into our industry careers, as graduation's right around the corner. So that's been a great way to connect with the industry and the standards set in the aerospace industry.
Very good. So we had a chance to view a few of the project highlights tonight, but is there one that stands out to you as your highlight from the project?
I think my highlight was seeing it fly for the first time. It's undeniably it was the peak moment for me of the Capstone career. Everything that you've worked so long for with the group, we've had some late nights, hard presentations, and finally you see what you built, what you designed, take off for the first time, and you're like, we did it. We really did it.
Yeah, I fully agree with that. I would love to say the same thing, but to add a different perspective, I'll add that I think my favorite moment was the canister drop, seeing that payload fall out of the plane for the first time, all the late nights and hours spent trying to make that payload deployment system work as best as we could, and then seeing it actually work in real life and watch the airplane continue flying and then have a successful landing. I think that was my favorite moment, and just really proud moment for the team too, to see all our hard work coming together and with a successful flight test. So,
and I'll just add that my highlight is just working with this team. I worked with dozens of teams over the years, and hands down, this is one of the best teams that I've ever worked with. Just seeing them come together and work effectively together and have a successful project's been just the reward for me.
Indeed, for me as well. We have lots of great questions in our chat, so we're going to turn our attention to questions that our audience has asked us. Starting with this one, what is an ombudsman? It was a role you saw on a slide, but I didn't speak much to it. Would one of you be willing to describe what an ombudsman is, how they helped our team be successful? Danielle?
I'm going to talk about this. This is a unique position on our team, which I think was actually really helpful to our team dynamics. An ombudsman was the person that we had specifically to help us deal with any team conflicts that we had, or interpersonal conflicts, or if we felt underutilized or overutilized by the team. There was a safe person we could go talk to and confide in, and you knew that they would have your back and help you address the situation and find a good resolution for all parties.
Thank you. Another participant asked about CAD. Do we use any CAD in our project?
Yeah, I can grab this one. We use CAD a lot. Thinking about all the hours spent on this project, it was probably a considerable number, especially for our structures team. So we had to CAD basically the entire airplane. So everything you're seeing there in that image of the airplane, every component on it was CADed, including all the off-the-shelf servos, the motor, even our landing gear, and then all the internal components too were CADed. So that work started very early in the first semester, and then refinements to the design, and using it as kind of our master model to get dimensions from, and help with material properties. Yeah, CAD was used extensively. So any experience in that would be heavily utilized for sure.
Indeed. What software packages did you use? What CAD packages?
Yeah, so the main tool that we used was CATIA. So there's a class 4 CATIA that a lot of freshmen can take if they choose their freshman year. Yep. And then also SolidWorks is used by some of the other engineering students, but CATIA was the main one that we used in our project.
Early in our presentation, we showed a flow chart with some code, and we talked about building this analysis tool that allowed us to rapidly evaluate different aircraft performance, aircraft configurations and their performance. But what if the code doesn't give you the right volumes or has an error in it? how did we troubleshoot? How did we ensure that we had reasonable results?
Yeah, I can take this one as well. So this is actually a great question because we did find a lot of different inaccuracies in the code as we were building it, and there was a lot of troubleshooting work required. So one of the ways that we validated this code was plugging in real airplane geometry into the code. And so we know the values for drag on those airplanes, for their thrust and their range and endurance. So plugging those values into the code, we could then output our code's version of that and then see if it was close or if it needed some tweaking. So there was many hours spent going back and tweaking the equations and fixing some of our assumptions in the code to try and make its performance as best as we could get it. So ultimately, we were able to refine it pretty well to where we could take an airplane, plug it into the code, and then actually get real results that made sense and that we were confident with to go forward.
Good. We have a question about our wind tunnel testing. Why did we use string and not paint or some other way to visualize the airflow?
I'd love to talk about this. So one of the main motivators for us to use the tufts or the string as our flow visualization is that the other options, so consider smoke or paint, could leave residue on the wind tunnel. And something we very recently got as of, I believe, fully implemented this semester is a brand new wind tunnel lab. And the one we used was a brand new wind tunnel. So it was very crucial to us and the faculty that run the wind tunnel lab that we keep everything in pristine condition. So there are a lot of great ways to do flow visualization. Like something we do in our wind tunnel lab is using a titanium oxide paint and painting that on and seeing what the vortices do on that and taking pictures of that. But that just wasn't an option with our brand new facilities.
Great. We have lots more questions in the chat. I'll try to pick out a couple more for us to explore. When in the designing phase, how do you figure out which designs are more achievable or overall will perform better?
Yeah, I can take this question. So one of the things that we did, and that also the DVF club on campus uses, it's called a method called trade studies. So this basically breaks down all of the different configurations of the airplane that we're evaluating, and we go through and assign a number, usually like 1 to 3, maybe sometimes 0 to 1, in terms of can we manufacture it? What's the aerodynamic performance? Is it favorable? Is it not? A bunch of other different criteria to kind of then add up all those numbers and see what configuration is the best. So this is a pretty visual and pretty easy way to down select your configurations. So we have a big team, so it was really easy to get a lot of discussion going and a lot of different opinions on why should we choose a T-tail over a conventional tail, or a propeller aircraft versus a jet. So evaluating all those configurations was done using trade studies.
Good. There are some questions about our payload deployment and our aircraft deployment. One has to do with whether we could deploy our aircraft from a variety of different larger aircraft, or if it's specifically designed for this particular aircraft. And then in payload deployment, whether we could deploy other types of payloads or not.
So I'll talk a little bit about our payload system and kind of how that works. We designed it specifically to operate with those 5-pound canisters, but a lighter canister still would be able to work. One thing about our system is it's designed to have a pin in it, and when the pin is pulled out, the cylinder will roll. So this specific design that we came up with does need to have a cylindrical shape, but it still could work if you substituted in different sorts of payloads and that kind of thing. It would just maybe need a little bit of tweaking.
Yeah, and then I can answer the part about dropping off different aircraft. So one of our requirements is we had to use a standard military lugs. So it's kind of hard to see, but on the top of the airplane, there's 2 lugs spaced 14 inches apart. And this is designed to interact with an ejector rack. So any military airplane technically that has that style ejector rack, this airplane could be pushed up onto, and then that airplane could go drop it. So the main design was for it to be dropped from the MQ-1 Predator drone, as we saw in the ConOps. But theoretically, it could probably also be dropped from an MQ-9 Reaper and some of the other larger drones that would be able to carry an airplane of this size. The all-up weight is right about 50 pounds for this airplane, so it's got to be a large airplane to be able to take our airplane up with it.
Indeed. I think we'll take one or two more questions. There's lots here, and I apologize in advance if we aren't able to make it to your question. But we'll take one or two more. First one is, what kinds of solo projects could I do now that would help my resume and help become more experienced for a capstone project?
I think one thing that could help you now before you even start college or attend Embry-Riddle and take any classes is really kind of learning how to use programming. That's something that's used a lot in our just day-to-day life as engineers here at Embry-Riddle. And there's a lot of YouTube tutorials, so it's very beginner friendly nowadays. Like you can get started, cost nothing, find free tutorials. And another way is if you have the capabilities to start kind of looking at CAD, because that is also another thing that we really take with us. And especially if you join any clubs such as RDL, DBF, you're really going to want to be familiar with that, either CATIA or SolidWorks or however you choose to get into it.
Thank you. And then a question, a fun question. What campus is best for aerospace engineering? I'd say both campuses have great aerospace engineering programs, so you can't go wrong. This evening, though, we focused on a project that we've done here on the Prescott campus. All right, well, thank you, panelists, for sharing this project. Congrats on the great work. And thank you to our audience for joining us this evening. Thank you for some good questions that spurred some great discussion. We hope to see many of you on campus here in the near future.